In this programme, we'll be looking at the gas tungsten arc welding process. We'll cover its history, the characteristics of the process, for what and where it can be used, the equipment required, and how to prepare for welding. The programme will be in 4 sections. Part 1 covers the principles, Part 2 the features, Part 3 the equipment, and Part 4 the working practices of gas tungsten arc welding. In a moment we'll be meeting Mel, who will take us all through the equipment and safe working practices. But first of all, the principles.
Of all the welding processes, gas tungsten arc welding, traditionally known as TIG, tungsten inert gas, is one of the most versatile. Not only can it be used manually or with automatic equipment, but it will weld a wide range of metals and thicknesses. It all began in the United States, where as far back as 1918, researchers were looking at ways of using gases to protect welds from oxidation. But it wasn't until 1940 that Northrop Aircraft pioneered the first commercial use for the gas tungsten arc welding process. They used it for welding magnesium for aircraft components using an inert helium shield. In the late 1940s, the process was marketed in the UK by the British Oxygen Company under the argon arc name, since the shielding gas used was argon. Since then, the basic principles of gas tungsten arc welding have remained unchanged, although equipment and consumables have been constantly refined and improved. Today, gas tungsten arc welding accounts for a market share of around 5% of welded carbon manganese steel and 10% of welded stainless steel. So what are those markets? Why do they opt for gas tungsten arc welding? And if it is so versatile, why is it not more widely used? To answer those questions, we must first look at the characteristics of the process. Gas tungsten arc welding uses the heat of an arc, which is formed between a non-consumable tungsten electrode and the workpiece to fuse the joint material. The arc area is shrouded by a shielding gas, which protects the weld pool and the electrode from contamination, while allowing a stable arc to be maintained. The welding arc is struck between a cathode and an anode, either of which can be the electrode or workpiece. A high voltage causes a flow of electrons from the cathode to the anode. This electron flow ionizes the gas. The ions are positively charged particles, so 2 types of charged matter flow between the cathode and anode. Electrons, which accelerate and bombard the anode, bringing it to fusion temperature. Positive ions. These are slower and move towards the cathode. The ionized gas increases the electric field, accelerating the electron avalanche. To support a stable arc, we need a high temperature at the cathode, sufficient voltage higher than the ionization potential of the gas, a gaseous environment providing sufficient positive ions. The temperatures in the arc vary and are typically 2,500 degrees Celsius at the cathode, 3,500 degrees Celsius at the anode, and 5,000 degrees Celsius in the arc column. Only about 40% of the arc energy is actually used in welding. The rest is lost by conduction into the workpiece, by radiation, by convection with the shielding gas. There are 3 modes of operation used in gas tungsten arc welding: DC electrode negative, DC electrode positive, and AC. In DC electrode negative, as the name implies, the electrode has negative polarity and the workpiece has positive polarity. So the electrode is the cathode and the workpiece is the anode. This mode provides a stable current and is the most commonly used. 2/3 of the heat is at the anode, the workpiece, and 1/3 at the negative electrode. It is used for most metals where the aim is to get as much heat as possible into the weld area without melting the electrode. With DC electrode positive, the electrode is positive and the workpiece is negative. This mode can be used for welding aluminium using pure helium as the shielding gas, where the helium arc has greater energy, and the action of the positive ions moving towards the workpiece disperses the tough refractory oxides of aluminium, which exist on the surface of the workpiece. Since most of the heat is in the electrode, larger diameter electrodes are needed, and care must be taken to ensure the molten end of the tungsten electrode does not contaminate the weld pool. In AC mode, the arc polarity changes with the frequency of the main supply. The arc is both DC electrode negative and DC electrode positive, with alternate half cycles, providing the heat to melt the workpiece and the cleaning action as the surface oxides are dispersed. This makes it an ideal process for welding aluminium, where oxides rapidly develop on the material surface. As the current is reversed, the arc is extinguished and needs to be re-established. This has presented some problems in the design of power sources due to effects which prevent the arc reigniting. Advances in AC welding power sources allow for simplified machines with improved arc characteristics and better arc reignition. Because of this, AC is now widely used for welding aluminium. To initiate the arc gap needs to be broken down to create the electron flow. There are 4 common methods for starting the arc. The early method, and one which is still used on most single-phase machines, is the scratch or touch start. This involves scratching the electrode onto the work to complete the current circuit and make an arc, then rapidly lifting it before the electrode fuses to the work. Unfortunately, however skilled the operator may be, tungsten contamination remains a constant threat. An alternative is the programmed touch start or lift start. With this method, you touch down with a very low initial current of around 1 amp to establish the arc without contaminating the weld. As the electrode is raised, the current increases automatically to the desired level. Another method is the high-frequency startup. By this method, a high-frequency spark rapidly ionizes the gas in the arc gap, which the current then uses as a bridge to strike the arc. Although this method is widely used, it is not without its own problems, causing interference with electronics such as computers, radio equipment and pacemakers, and its use is thus being phased out. The 4th method is to use DC voltages of around 10,000 volts, but these can be a serious safety hazard, and so this method is only used in automatic systems where the operator is protected from the high voltage supply. As we have just seen, the arc is very hot and localized, allowing the heat to be applied in a small area. The arc can easily be controlled by varying the welding current, travel speed, and by adding filler wire. Because the welder has accurate control, he can produce a high-quality weld with no spatter. The finished weld is neat and clean and needs no post-weld cleaning, so reworking and rejection are kept to a minimum. Although gas tungsten arc welding is a slow welding process, it does produce high-quality joints. This makes it attractive for demanding applications where product quality is important. But to produce the high-quality weld, the operator needs to have more skill than operators for other welding processes. One of the most widely used applications for gas tungsten arc welding is pipe fabrication, where the highly controllable process lends itself to the critical job of root runs. Other applications include the nuclear, aerospace and petrochemical industries, where weld strength is vital for safety. The food processing and brewing industries, where a smooth weld finish offers no hiding place for bacteria, and in the fabrication of sheet metal for display cabinets, where finished appearance is all important. Many of these applications share a common characteristic, that is, their use of stainless steel or aluminium, metals which require a higher skill level to weld than carbon manganese steel. Other metals like copper and nickel alloys and reactive metals such as titanium and zirconium are also suitable for gas tungsten arc welding. Carbon manganese steel is less commonly welded using the gas tungsten arc process, except for critical route runs. Depending on the application and budget, the operator can choose either manual or automated gas tungsten arc welding. Manual welding is by far the most commonly used method and requires both good judgment and a steady hand. The judgment is in deciding what heat input is necessary to melt the metal and achieve penetration. The steady hand is needed to guide the weld along the seam, keeping it within the area required. Mechanized gas tungsten arc welding is growing in use as costs allow. A wide range of systems is available, from semi-automatic to fully computer-controlled. But all share the advantages of increased productivity, consistent weld quality, and improved operator safety. Indeed, by nature of its cleanness and controllability, gas tungsten arc welding is probably the most suitable process for machine and automatic use. Orbital welding is a technique by which the electrode is clamped onto a welding head and travels around the outside of a fixed pipe or tube weld seam. The technique produces consistent, high-quality welds and is useful where a component can't be moved and access is difficult, although the high cost of these systems does make them most suitable for large volume production and very high-quality work. Depending on the application, the operator can also choose between the autogenous or filler wire method. With autogenous welding, the weld is formed by the fusion of the parent metals without the addition of filler wire. This technique gives a very neat weld finish, but is only suitable for particular applications, usually the welding of thin sheet metal. Usually, the filler method is required to achieve sufficient weld strength, and the filler is added into the weld pool in the form of a rod. The filler wire can be heated via an additional power supply. This is known as hot wire gas tungsten arc welding. The use of hot wire means that there's no cooling effect in the weld pool, hence traveling speeds and deposition rates are increased. The process can either be used manually or automatically. It is most suitable for automated welding, where the wire can easily be orientated with respect to the joint.
Well, for the purpose of this programme, we'll be concentrating on the manual gas tungsten arc welding process. Mel's going to show us through the equipment, aren't you?
The main components for the process are a power source, a welding torch, a supply of shielding gas, filler wire for the weld, and the connecting cables.
Right, fairly straightforward on the surface. The power sources come in various sizes, though, for different applications, don't they?
Yes, they do. We have small amperage, single-phase machines, such as the one behind you. These are used for DIY or light industrial use.
Yeah.
This one is an industrial machine. This is three-phase supplied, and in this case, the welding output is 350 amps, but they can be larger.
Right, so let's go through to the controls of this one. This is obviously on-off.
Power supply on-off.
Yeah.
We then have the electrode polarity switch. This determines whether we're going to use AC welding current or DC electrode positive or DC electrode negative.
Right, and what would you use for this process?
This process, we're mostly going to be using DC electrode negative.
Right, what about this meter?
Current control switch, the display on the top shows the welding current that's going to be used.
Okay, and high frequency there?
High frequency is used to initiate the arc. When we're welding with DC, we'll use start selection. This means that the high frequency will switch out as soon as the arc is established. Continuous is used for AC welding.
Okay, obviously you need to control gas. How do you do that on this machine?
There are two timer switches, a pre-flow and an after-flow switch, and these determine the amount of gas that's going to be used before the arc is established and after it's extinguished.
And there's even an option to control the current at the end there, I see.
The current control can either be local, whereby the switch on the torch will establish the arc, or we can use the remote setting whereby the welder can vary the current used by means of a foot switch.
Okay, final piece of the puzzle
Is the earth clamp. This lead now completes the electrical circuit back to the machine.
Right, let's move through to the next room, Mel. You can take me through the components of this torch now. Right, Mel, well away from the welding room, here in the cleaning room there are other elements of the puzzle to put together. What's first?
We mentioned the torch earlier on, so let's have a closer look at this. This is a water-cooled torch that we're using. So we have a water inlet and a water outlet. The water inlet also picks the power up, so the welding power is going to go through this cable. We have the gas supply in, and you'll notice that the size of the nuts is different from the water supply, so there can be no confusion.
Yeah.
The other lead coming down, we have no plug on because we're using this torch on a remote-controlled foot switch, but this lead, if it had a plug into the machine, would allow the switch on the torch to be operated.
Right.
We come up to the welding head, and the first part to be fitted is the collet holder. You can see the collet holder has holes in the side. This is where the gas is going to come out inside the ceramic nozzle and be projected forward. It also has a gasket there to prevent any gas leak. So we just fit that in. And into the back of the collet holder go the collets to hold the tungsten. There are various sizes of collet for the various sizes of tungsten that we're going to use. We'll fit this one, which is a 2.4 tungsten. Just fit loosely into the back. Screw the tailstock lightly in.
That also has a seal on the back there as well.
Again, to prevent any gas escape. And when it's more or less in place, we can select the ceramic nozzle. Now you see again there are different diameters of ceramic nozzle. Loosely, the smaller diameters will be used on lower amperage work and the larger diameters on higher amperage work.
Yeah.
But access to the job may be a problem, so you may use a smaller diameter nozzle to get into a restricted corner. Fit that onto the front. When it's in place, we can determine now how much tungsten stick out we need from the end of the nozzle.
How critical is that?
It's critical to provide sufficient gas coverage for the weld. So a stick out of maybe 8mm, that would be suitable for fillet welding. If we wanted to weld a butt weld, we might need slightly better gas coverage, so we'd push the tungsten to maybe 6mm stick out. There is a different design of collet holder, which is called a gas lens, and here is one. This is for a smaller torch than the one we're showing here. The gas lens provides a lamellar gas flow so that you could have tungsten stick-outs of maybe 20, 25mm and still provide adequate coverage to the joint.
Right. OK, so onto the tungstens themselves now.
The tungstens themselves are mixed with rare earth elements such as zirconium, thorium or cerium. For AC welding, zirconiated tungstens are recommended. For DC welding, then thoriated tungstens are recommended. The rare earth elements are actually providing a stable arc and also aiding the arc initiation.
Right.
The grinding of the tungstens with AC welding, it really is necessary just to grind off the end of the tungsten because as the AC arc is formed, so it will produce a ball on the end of the tungsten, such as this one. With DC welding, however, we grind to a point. Loosely, the smaller the diameter of tungsten, the sharper the angle of point, maybe a 30-degree included angle. As the current raises, so tip retention becomes a matter, and we have a broader tip ground onto the tungsten. We have the tungsten grinder there. This is a dust extraction system because there is concern over the low level of radioactivity from thorium. So the grinding dust from the thoriated electrodes may provide a problem. So the fume extraction system takes the dust away.
Yeah, bit of safety kit with that is...
you must have goggles, of course, whenever you're grinding.
Yeah.
The seriated electrodes are being brought in now because there is no radioactive problem with them.
Right, and as you said, these are colour-coded, aren't they?
They're all colour-coded, zirconiated having the white tip, thoriated having the gold tip, and the seriated having a grey tip.
Fine. One of the major jobs you do in here is clean, of course.
Clean the material. We have aluminium here, which looks reasonably clean, but there is certainly a grease on the surface, probably from the protective wrapping that gets put on aluminium before it's supplied.
Yeah.
So we degrease this using a solvent. We always recommend acetone. Paper towel to clean rather than rag, and the acetone should be stored in a squeegee bottle for ease of use.
Right.
Other cleaning material, use a stainless steel wire brush for aluminium, and there's also wire wool or scouring pads to provide extra cleaning for this, but also maybe for the filler wire as well.
OK, that's fine. Thank you, Mel. Let's now go back to the welding area. Right, Right, Mel, back into the welding area. You obviously can't weld without welding rods, and here are some.
Yes, this is a filler wire. It comes in a range of diameters to suit whatever job you have. Also in a range of materials to suit the material of the job.
Right.
So here, for example, we have mild steel, stainless steel, and aluminium filler wire. They come in standard lengths, 750 millimetres, and it's added to the front of the weld pool.
Right, that's fine. For the moment, Mel, thank you very much indeed. Now, though, we'll move on to the final part of the welding equation, the shielding gases.
The most widely used gas is argon, but other gases are added to improve the properties of the shielding gas. The shielding gas performs several important functions. It protects the weld from atmospheric contamination. The flow rates of the shielding gas need to be adjusted correctly to provide laminar flow, so that the surrounding air is excluded from the weld pool. This can be aided by using gas lenses in the welding torch, which smooth out the gas flow. Too low a flow rate and the weld pool is not shielded due to insufficient shielding gas. Too high a flow rate and the gas flow becomes turbulent, pulling in the surrounding air. In the gas tungsten arc welding process, it also prevents the oxidation of the tungsten electrode. And for this purpose, inert gases such as argon and helium are used. Small additions of reducing gases, such as hydrogen, can be added without affecting the electrode. It stabilizes the arc. In these stainless steel welds, you can see that an argon-helium-hydrogen mixture, as used on the right, gives a more stable arc than argon, as used on the left. It controls the weld bead shape and penetration. Hydrogen is often added to argon in small quantities, usually between 1 and 5% hydrogen mixture. As these macrographs for argon on the left and argon-hydrogen on the right show, the increase in the arc temperature with the hydrogen results in better penetration and improved weld profiles. It affects weld metal chemistry. These two macrographs of welds in duplex stainless steel show the addition of nitrogen to argon helps maintain the balance of austenite and ferrite, whereas the use of argon promotes the growth of ferrite, which is detrimental to the impact properties and corrosion resistance of the metal. Influences the economics of the weld. The addition of helium and/or hydrogen to argon increases the arc temperature, which allows for faster welding. Since hydrogen is a reducing agent, helping to prevent oxidation, it gives a cleaner finish to the weld, removing the need for post-weld cleaning. We'll be looking at practical gas tungsten arc welding applications in future programs in the series. For now, let's consider the working practices.
Right then, Mel, so what are the best working practices?
The first would be to have a clear working area, so we just move the filler wire out of the way. And the material to be welded itself should be free of any grease. For this, we'll use a solvent, so this should be done away from the working area because of any flammability problems. It's also a good point to wire brush immediately prior to welding to break up the oxide surface. For this, we'll use a wire brush, stainless steel for stainless steel and aluminium, and mild steel for mild steel. It's a good idea to keep the wire brush suitable only for that material.
Fine. What about the gear? We've got strong overalls on to start with, haven't we?
The arc is going to emit radiation, which can burn the skin, so we wear overalls to protect the skin. Similarly, leather gloves to protect the hands. These are quite a thin leather to aid us with our feel for the process, particularly on the filler wire. We also will wear a head shield with a filter so that we can view the screen, and the sides to protect our face from any burning.
Fine. And ventilation's obviously very important with the fumes coming off.
Welding fume may be hazardous, so we always recommend that you use local extraction of this type to take any fume away.
Fine. Now, purging, I understand, is very important, isn't it?
Indeed, the surface of the weld where the torch has been is going to be well protected by the gas shield, and so will not have any oxidation. But the reverse side, particularly on stainless steel, will almost certainly have oxidation. This can lead to corrosion problems. With a pipe, we would fill the pipe with a purged gas,
Yes.
so that we have no corrosion problems on the bag. This would be particularly important in the food industry, for example, where any corrosion can lead to microorganisms in the crevices.
OK, so that's nice and clean and sterile as far as you can get it inside. We'll set up for some welding in a few minutes' time, but Mel, thank you very much indeed. That brings us to the end of this programme, Gas Tungsten Arc Welding, Process and Practice. In it, we've looked at the principles of the electric arc, the current modes used and what they're used for, also how the arc is established. We've looked at the features and the equipment and explained why the process is used for its many applications. The practical aspects of gas tungsten arc welding are covered in other programmes in the series, which deal with the basic skills and the welding of individual materials. So, Mel, let's set up. Shall I get some more?
You have just seen one of an expanding series of BOC training videos, which cover a wide range of cutting, welding and safety-related topics. To find out more, call free on 0800 515 661. That's 0800 515 661.